Marcus, what are you doing here? You need to be taking the test. Don't get me wrong, I'm happy to see you. Is there anybody else in here who needs to be doing the makeup test? So remember, the makeup test for exam 3, the I had tech issues makeup exam for exam 3 is going on during class time today, like right now. It opened at exactly 11 o'clock, and you access it by going to Canvas, clicking on our class, going to HonorLock, and then launching HonorLock proctoring just the same as you would last Friday. Okay, so if that's you, or if anybody else here needs to be doing that, please go ahead and sign out of this meeting and go ahead and get that done. Today is the last chance to take exam 3. So hopefully everybody else here is ready to rock and roll, and we can talk a little bit more about systems of equations. You do not need to see my bagel, but you do need to see the mathematics. Okay. So this is MAC1105. Section 007, lecture 2220. And today we're going to talk about systems of equations more. Last time we saw two methods for solving systems of equations, and we categorized systems of equations into two categories. So there are linear systems and nonlinear systems. Remember, linear systems that is a collection of equations meant to be solved simultaneously, i.e. a system. This is a system in which all the equations are linear. And if you need to remind yourself what it means for an equation or a function to be linear, you might want to go back and look at the first few homeworks from this semester, where we categorize things as being linear and nonlinear. But the basic idea is that the variables all show up only to the power of 1. They never show up under a radical or downstairs in a fraction or anything like that. And these are nice. We like to solve them by elimination wherever possible, and it's always possible. And then the other category were nonlinear. Nonlinear system of equations. This is a system in which any one equation is nonlinear. And all sorts of things can make an equation nonlinear, like just having one variable raised to the power 2, or having one variable under a radical, or having any variables downstairs in a fraction, or having any variable raised to any power other than 1. These are not so nice. Meaning the theory behind them isn't as clean as the theory for linear systems. And on Friday, we're going to talk a little bit about the theory behind linear systems. And these we have to solve with substitution. You can use substitution to solve linear systems also. It's just not wise to do so. It takes longer, it's messier, and as the size of the linear system gets larger and larger, the substitution method gets clumsier and clumsier, whereas the elimination method is always nice. Now I have here a breakdown of the two methods that we're talking about. So the method of substitution is one that I think pretty much everybody is familiar with from high school. That is where you pick an equation, you pick a variable, and you solve one of the equations for one of those variables. Say you solve the first equation for y, and that'll give you something like y equals 7x minus 5. Then you take that and you plug it in the other equation. So you take your y equals 7x plus 5 or whatever, you go to your other equation, and anywhere there's a y, you write 7x plus 5 instead. That means that that other equation now only has one variable in it. In the example I just mentioned, that second equation would now only have the variable x, because everywhere there is a y, you plugged in 7x plus 5. Now that that other equation only has one variable, you can solve it explicitly, meaning you can get a number out for that variable. So you go ahead and do that, get that number out, and then you back substitute that number into either of the original equations. So like here, I would have solved that second equation for x, and I would have gotten a number. And then I would take that number and I would plug it back into either of the original equations to get y. It works, and it's reasonably intuitive, but it's slow, it's clunky, there's a lot of places to make mistakes, and it does not generalize well. That's the big thing. So if I give you a 3x3 system or a 4x4 system, solving that system by substitution would be hell. So instead, we need to learn about elimination. Elimination is where you multiply through one of the equations by some non-zero constant to make the coefficient of one of the variables the negative of the coefficient of that same variable in the other equation. So if I have something like x plus y equals 1 and 2x minus 2y equals 5, and then I can multiply through that first equation by 2, and so that would make the coefficient of y in the first equation 2, and the coefficient of y in the second equation is negative 2. So that makes the coefficient of y in the one equation the negative of the coefficient of y in the other. That's our first step. Multiply through one of the equations by whatever constant you need to in order to make one of the variable's coefficients the negative of that same variable's coefficient in the other equation. Then you add the two equations together. Since you just did this, when you add those two equations together, one of the variables will go away. Like if I had 2y in the first equation and negative 2y in the second equation, then when I add those, I'll get 0y. And so the result would have just x's. Solve that equation for x, or whatever variable you didn't eliminate, then back sub to get the other value. Much cleaner. So today I want to get a little bit more practice with this. The catch is that I've got people taking the makeup exam right now, and those are the folks who had tech problems when we did this Friday, so I'm anticipating more tech problems now. So if you'll be patient with me, I'm going to be tabbing back and forth to my email to make sure everything goes okay. Yeah. Okay. Looks like so far things are going all right. So let's then go ahead and take a system and solve it. Solve it by elimination. Let's solve this system. 1/2 x minus y equals 3, and 3x plus 2y equals negative 1 by elimination. So I'm choosing these numbers so that this example is not quite as easy as the example we did last time. Here we will have to deal with some fractions as we go through this, but it's still the same sort of thing. I have to multiply one of these equations by a non-zero constant in order to make one of the coefficients, say the coefficients of x, negatives of each other, or the coefficients of y, negatives of each other. I could multiply through the first equation by a -6, and that would make this -3x, so that when I added it to this, the x's went away. Or I could multiply through this equation by +2. That would make this guy a -2y, so that when I added it to him, the y's went away. Or I could multiply through the second equation by +1/2. That would make this become a +1y, so that when I added these, the y's would go away. Or I could multiply through this equation by a -1/6, and that would make this a -1/2x. So when I added it to this, they would go away. I think the cleanest choice is to multiply through this guy by 2, because that will get rid of the fraction in front of the x, and it will also set me up to eliminate the y. So let's do that. My first step, the first equation by 2. So when I multiply through that first equation by 2, the second equation doesn't change at all. He stays 3x plus 2y equals -1. And one of my little bits of advice for solving systems, write down the shit that doesn't change first. When I multiply through the first equation by 2, 2 times 1/2 x, that's just x. 2 times -y is -2y, and 2 times 3 is 6. And since we chose the constant and the equation to multiply by cleverly, this coefficient is now the negative of this coefficient. So when I add these two equations, the y's will all go away. Getting some more panic emails, so let me see. Yeah, okay, that's all fine. So now I'm going to add the two equations. And the nice thing about this is that you can kind of like think of it, just like this. You're just going to add the columns. So x plus 3x, that's 4x. -2y plus 2y, that's 0y. And 6 plus -1 is 5. So in other words, I have here 4x equals 5, which means x is 5/4. So just like that, I get the x-coordinate of my solution point. Now I backsub x equals 5/4 in either equation, either original, to find y. In truth, you could backsub this into any of the equations that we've had that have both x and y in them, because they're all equivalent. But let me go ahead and take this and plug it back into this guy. So I'm going to plug this into the second equation, 5/4 for x. So I get 3 times 5/4 plus 2y equals -1. 3 times 5/4 is 15/4. And now to solve this for y, I would subtract 15/4 and then divide by 2. So this is the same as saying 2y equals -1 minus 15/4. And now to deal with those fractions on the right-hand side, I have to have a common denominator. -1 is the same as -4/4. So this is 2y equals -4 minus 15 is -19/4. And now I divide both sides by 2, which is the same as multiplying both sides by 1/2. So I get out here y equals negative 19 over 8. So this is the y value, and this is the x value. So the solution to the system is the point 5/4, comma, negative 19/8. And what you'll notice is that this is not the sort of solution that you could ever see just from graphing, right? We would never be able to guess these numbers from the picture, even if your picture is very nicely drawn, even if your picture is drawn by Desmos or by Wolfram Alpha or by some other software. You're still going to be looking at decimals, you're still going to be kind of guessing. So it's important that we get comfy with this method. So take a look at what we have here and see if you have any questions about what we did, how we did it, why we did it. Make sure that you can follow the whole process. So we began with this system that I wanted to solve by elimination, and I decided to eliminate the y's. In order to eliminate the y's, I realized I needed to make the coefficients of these y's negatives of each other. The coefficient of y in the first equation is -1. The coefficient of y in the second equation is +2. So in order to make these coefficients negatives of each other, the easiest thing to do is to multiply this guy by 2. But if I want to multiply him by 2, I have to multiply everything in that equation by 2. 1/2 times 2 is 1, so 1/2 x becomes x, minus y. If I multiply that by 2, that becomes minus 2y. 3, if I multiply that by 2, that becomes 6. So I get this new system, which is equivalent to the original system, because all I did is multiply on both sides of this equation by a constant. We know we're allowed to multiply on both sides of equations by constants. It doesn't change anything. Then I add these two up. I add this equation to this equation, and the y's go away. So that gives me a simple equation that I can solve for x. Then I take that x value, and I back substitute it into either of the original equations to find the y value. So I'm just plugging x equals 5/4 back into either of the original equations. I chose the second one to find y. And from there, it's just a very simple linear equation that I can solve for y. I want to get y alone, so I subtract 15/4 from both sides. I have a common denominator. 1 is 4/4, so -1 is -4/4. -4 minus 15 is -19, so that's -19/4. And then I divide both sides by 2, which is the same as multiplying both sides by 1/2. When I multiply on the left by 1/2 here, 2 times 1/2 is 1, so this is just y. And -19/4 times 1/2 is -19/8. Any questions on that process? Okay. So solving 2x2 linear systems using elimination is not terribly hard. The next thing I want to talk about is the possible solution cases. So how many solutions can there be to a linear system? This is actually a question we can answer really satisfyingly, very thoroughly. And you can get there just by thinking about the geometry. remember, the solution to the system is the point or points where the graphs intersect. And since we're just asking about linear systems, there's only 3 ways for lines to intersect. It's possible that the lines don't intersect at all. It's possible that the lines are parallel. And they never intersect. i.e., the system has no solution. We call this a dependent system if the lines are parallel. And we would also refer to the system as being inconsistent, as having no solution. I don't think your homework uses the dependent-independent notation or terminology, but they will talk about whether a system is consistent or inconsistent. If a system does not have a solution, then we call it inconsistent. Another possibility is the one that we've seen mostly so far. The lines are not parallel. Maybe something like this. So here you have a unique solution. So there is one and only one solution. Such a system we would refer to as being consistent. And also independent. But I think back in 1033, some of the homework uses the dependent and independent terminology, but in 1105, we don't care so much about that. But if you're curious, yeah, this would be an independent system because those lines, we would say those equations are linearly independent, which has a deep meaning in the linear algebra class, but since we don't talk about linear independence in any other setting, I don't see a reason to stress you guys about it here. But if the two lines are parallel and distinct, so same slope but different y-intercept, then you're in case 1 and you have no solution. If the two lines have a different slope, then you're in case 2 and you have a unique solution. You can see here that I've left some space for a case 3. Is there anything that's not covered in these two cases? What if the lines have the same slope and the same y-intercept? So maybe here's the first line, and then, here's the second line. Same slope and same y-intercept. Yeah, they're identical lines. So we really don't have two lines, we really just have one line. Well, how many places do those guys intersect? Yeah, everywhere. So these guys, they intersect everywhere. Or intersect at infinitely many points. So we'd say there are infinitely many solutions. So one of the questions we should be ready to answer is, how do you know which one of these cases you're in? Of course, you can always graph the lines. This, by the way, we would refer to as being consistent and dependent. Consistent because there is a solution, but also dependent because the two lines are not they're not linearly independent. We don't know what linearly independent means unless you had a really good 1033 teacher. So if that's terminology you haven't heard before, don't stress it. So a system is called consistent if it has a solution, and it's called independent if the two lines have a different slope, otherwise it's called dependent. I'd like to know how to tell which one of these cases I'm in ahead of time, and maybe I'd like to be able to do that without graphing. I'd also like to have a way to write down the solution set in case 3 here. Just because there are infinitely many solutions doesn't mean every ordered pair x comma y solves, right? If I took a point out here that's not on the line, this point would not be a solution to the system that we've drawn here because it's not a place where those two lines intersect. So the solution set here would be the set of all these points on the line. The solution set here would be just this one point, and here there would be no solution set. We know how to write down the solution here. This is the sort of thing that we just did an example of. There's nothing to worry about here. You just say there's no solution, but how do you write down the solution set here? That's a different matter altogether. I'm gonna take a quick look back at my email to make sure there aren't any people panicking while they're taking their tests. Oh, seems to be going okay. All right. So let's solve the system. Two x plus y equals 4, and negative x minus 1/2 y equals negative 2. Let's solve this by elimination. So I claim that this is a dependent system, that if you graph these two lines, you'll see they have the same slope. And I would be interested to see what happens if I try to run my normal elimination algorithm here. That is, I multiply through one of the variables by a constant to try and make it the negative of the constant associated with the other variable, and I add them. So if I wanted to eliminate the x's, I could multiply through this guy by 2. And what I get here is the new system 2x plus y equals 4. And then negative x times 2 is negative 2x. Minus 1/2 y times 2 is minus y. And negative 2 times 2 is negative 4. So this is what I get when I do that. Now if I add the two equations, something interesting happens. Negative 2x plus 2x is 0x. Y plus negative y is 0y. And 4 plus negative 4 is 0. Interesting, right? So the left-hand side is 0 and the right-hand side is 0. Which is a true statement. Regardless of x and y. And this is what tells me that I have infinitely many solutions. But how do I write them down? Because like we said, just because you have infinitely many solutions doesn't mean every point x comma y solves. Like in this picture, this system would have infinitely many solutions, but this point, for example, is definitely not one of them. So how do I classify the ordered pairs which solve that system? Well, it's any point that's on the line, right? If those guys are both the same line, then any point on that line solves the system. How do I classify a point on the line? Well, it's x comma y, where x and y satisfy one of these equations. So let me take the first equation and write it as y equals negative 2x plus 4. Then my solution set is the set of all points x comma y on the line. And the way I write that, the set of all points x comma y that live on this line is, I could write it like this. I could say it's the set of all x comma y such that y equals negative 2x plus 4. That's one way to do it. But a nicer way to do this might be as the set of all ordered pairs x comma negative 2x plus 4, where x is any real number. Especially in pre-calculus and beyond, we like to see the solution set written like that. I would accept either on a test, but in my math lab, you need to be prepared to look for solution sets that look like this. You understand why we're looking at solution sets that look like this? Why these two are the same? This is all ordered pairs x, y, where y is equal to negative 2x plus 4. So here I've just replaced y by what it is, negative 2x plus 4, and let the reader know that this works for any real number x. Questions about that? Okay. So, I don't want
if you
yeah, go ahead.
I'm gonna say if you put a 2 into that equation you just wrote, I don't know, I probably did it wrong in my head, but it looks like it came out with an 8. Would that have been right for the y?
You're saying if I put in 2 for what?
Like for x.
So if you want to find a particular point to solve,
like to find a specific point for the negative 2x plus 4.
so that would be 2 comma negative 2 times 2 plus 4. Negative 2 times 2 is negative 4. Negative 4 plus 4 is 0. So one that solves that system, and it's just one of the infinitely many points that do, is 2 comma 0.
Okay, I got you.
Yeah, so don't forget the negative in front of this 2, right? Without that, you would get an 8 there, but it's negative 2x plus 4.
All right, that makes sense. Okay, yeah, I got an 8. Thank you.
That's all right, yeah, no problem. So I don't want to venture too far away from this topic, and specifically, I don't want to start talking about systems of inequalities yet. We're going to save that for Friday to try and keep you on track with my other class. But I would like to look at an inconsistent system, see what those look like when we try to eliminate. So let's do something like and about this. Okay. So I've got 2x minus 6y equals 0, and negative x plus 3y equals 1. And I want to solve this by elimination. Same sort of deal. I'm going to multiply through one of the equations by a constant, chosen to make the coefficient of one of these variables the negative of the coefficient of that same variable in the other equation. So if I wanted to eliminate the x's, I could multiply through this equation by 2, and that would make the coefficient of x here negative 2, while the coefficient of x here is positive 2, and so those would be negatives of each other. So let's multiply equation 2, the second equation, by 2. And what I'll get there is 2x minus 6y equals 0. And then down here I'll have negative 2x plus 6y equals 2. So now this and this are negatives of each other. And when I add them, I'll get 0x, negative 2x plus 2x, plus 0y, equals 2, i.e. 0x plus 0y, that's 0, equals 2. So the last example when we did this, we ended up with a 0 equals 0 at this step, which told me I had infinitely many solutions because that's a true statement regardless of x and y. Here, I get 0 equals 2, which is a false statement independent of the choice of x and y. So this is, which is false, no matter the choice of x or y. In other words, this is a contradiction. This is a statement which is not true, and it's logically equivalent to our system, which means our system, if this system had a solution, then 0 would be equal to 2. Therefore, the system must not have a solution. So our system can't possibly have any solutions. And that's kind of the whole picture, guys. I mean, at least when it comes to 2x2 linear systems. So nonlinear systems can get difficult, and those we always have to solve by substitution. We can't expect to eliminate in a nonlinear system, but in a linear system, you can always run this elimination process. If you're in that nice case where you have a unique solution, then the elimination procedure will get you that solution faster than anything else. And if you're in either of the other two situations, where either there's no solution, like here, or there's infinitely many solutions, like in the previous example, elimination will discover that for you also. So for so many reasons, elimination is the way to go. It's the best way to detect which case you are in, and it's also the best way to find the solutions in the cases where the solutions exist. Any questions on these three little examples here? Okay. Then since we have time, I would like to work one more nonlinear system with you. We only got to do one of those last time. Mm-hmm. And let's do, let's do this, Okay. So this is a nonlinear system because in that first equation, one of the variables is being raised to the power of 2, right? So that first equation is not a linear equation, which means that this system is not a linear system. In order to solve the nonlinear system, I use substitution. So solving the second equation for y, say, I get y equals negative x minus 3. And then I can take that and plug it into the first equation. Let's see, is this going to be good? Tell you what, let me make a small change here real quick. I just want to check something because I am cooking this up off the top of my head. Right. Yeah, let me change that minus 3 to a plus 3. Sorry. Do me a favor, come back here to this step. Change the right-hand side of that second equation to plus 3. That will change this to a plus 3. It'll be a better problem this way. All right. So we're going to substitute. My system is x minus y squared equals 0 and x plus y equals 3. If I take the second equation and I solve it for y, that means I'm going to subtract x from both sides. I get y equals negative x plus 3. Now I'm going to substitute negative x plus 3 for y in the first equation. So that becomes x minus negative x plus 3 squared equals 0. And I have to FOIL this out. So that will become x minus negative x times negative x is positive x squared. That's my firsts. My outers, if I multiply negative x times 3, I get negative 3x, and I'll have that twice, so I'll get minus 6x. And then my last 3 times 3 is plus 9. So this is what I get when I square negative x plus 3. And now I can combine my like terms. I'm going to distribute this negative. And that gives me negative x squared plus 6x plus x is plus 7x minus 9 equals 0. And this quadratic equation I can try to solve by factoring, or I could solve by using the quadratic formula. Maybe I would start by dividing both sides by -1 to get rid of the negatives. So this is the same as x squared minus 7x plus 9 equals 0. And then if I wanted to factor this, I would have to find two numbers that multiply to 9 and add up to -7. I don't think you will find those. I don't believe those exist. 9 is 3 times 3 or 9 times 1, and that is it. And no combination of those add up to -7. So from here we would need the quadratic formula. Four times 1 times 9 is the same as 4 times 9, which is 36. Oh, no, it's not. Yeah, it is. Yeah, 40 minus 4. All over 2. Let's see, did we do that right? Yep, yeah, so x equals negative b. B is -7, so negative b is 7. Plus and minus the square root of b squared, well, -7 squared is 49, minus 4 times a times c is 4 times 9 is 36, all over 2. So that means x is equal to 7 plus or minus 49 minus 36. Let's see, that's 4 plus 9, is that 13? No, let's see. Yeah, so to get to 40 from 36, we need 4. And then to get from 40 to 49, we need 9. So that's 4 plus 9 is the square root of 13 here. All over 2. So we have these two x values. X equals 7 plus the square root of 13 over 2, and x equals 7 minus the square root of 13 over 2. But remember, the solution to the system should be an ordered pair, should be an x value and a y value. So here, what I'm seeing is I think there will be two solutions. There will be a point associated with this x value, and there will be a point associated with this x value. So one solution, I can now back sub this to find y. And I'll back sub into the simpler equation, the linear equation. So I'll have 7 plus the square root of 13 over 2 plus y equals 3. And then you can solve this by subtracting that quantity over there. That's the same as saying y equals 3 minus 7 plus the square root of 13 over 2. And we can actually clean this up. That's the same as saying y equals 3 minus 7/2 minus the square root of 13 over 2, and you can put these together. 3 is the same as 6 over 2. So 6 over 2 minus 7 over 2, that's negative 1 over 2. So this is negative 1/2 minus the square root of 13/2. So one of my solutions is this comma this. And the other solution I would find by doing the same thing, just with the other x value there. So to find the solution from this guy, I'll take that x value and sub it back into equation 1. That would be 7 minus the square root of 13 over 2 plus y equals 3. Again, I subtract that over, so I get y equals 3 minus 7 minus the square root of 13 over 2, which is the same as saying y equals 3 minus 7/2 plus the square root of 13 over 2, just distributing the negative and splitting up the fraction. And then from here again, 3 I can think of as 6/2. This is 6/2 minus 7/2 is negative 1/2 plus the square root of 13 over 2. So the other solution is ordered pair 7 minus root 13 over 2, comma, negative 1/2 plus square root of 13 over 2. Okay, so any questions about this last system? This is about as bad as nonlinear systems will ever get for you guys. I won't beat you any harder than this. And the important thing is that you get comfortable using the elimination technique to solve the linear systems. That's what the bulk of your homework has you doing, and that's by far the most important of these things to learn how to do. Nonlinear systems are fun and interesting in their own ways, but it's nowhere near as important as linear systems. And especially when it comes to linear systems, it's very important you get comfortable with the elimination method. That is, we're a little bit over time now, so I think that is where I'm going to chop the class for today. Any other questions? Questions about testing or how the semester is going to wrap up, anything like that? I do know some people are waiting on me to get some things graded, some makeup stuff from earlier in the semester and some later handed in things. And I'm sorry I haven't gotten to those yet. I really am doing my best to get through all this stuff, but you know, shit is crazy. I will get everything in there as soon as I can for you guys. And if you're waiting on something that's driving you nuts, don't hesitate to send me an email or a Canvas message reminding me. But is there any questions or concerns about?
Yeah, I was talking about sport.
Say that again?
I was just wondering a little bit about how test 4 is going to look. Are we going to do a separate like project or test on systems of equations this week or next week? Or are we just going to chop it and kind of go with the final?
No, at the end of this week, I'm going to give you test 4. It's a take-home test. It'll be like similar to one of our projects. So I'm going to give you a take-home test on Friday, which will be due on the day of the final.
Understood. Thank you.
Cool. Any other questions about that stuff? I'm glad you asked. This is sort of things I don't want you guys stressing about them. So anything else like that on your minds? Okay. Then I will go ahead and end the meeting here for today. If you are curious about anything or have questions about anything, the final exam, exam 4, grading stuff, anything like that, don't hesitate to ask. You can send me a message on Canvas. I do have an office hour tomorrow. If you want to talk to me about anything at all, feel free to drop by the office hour, send me a Canvas message or an email, whatever you're comfy with, okay? I hope you guys have a pleasant rest of your day.